Welcome to my channel. In this video, we are going to show you how to calculate or how to find the magnetic field of a current carrying conductor at a point away from that conductor. Now, this is the point we are interested in. The current is flowing through this conductor, and this is the small change in length. The contribution of this small change in length at this point is given by this formula, and this formula is known as the Belt and the Savart law. Okay, now what we have is the mu naught, the current flowing through it, and the small change in length sine theta all over 4 pi r squared, where our r squared is coming from this one. Okay, we have two angles. What you should know is that when the current is entering this point, it meets this angle, and when it is leaving this point, it leaves this angle behind. These two angles, we want to know which of them is the right one to use. The right one to use is the one you leave behind when the current gets to this point. When the current leaves this point, the angle it leaves behind is the right angle to use, which is theta. So that's why we have theta. Please always take note of this. So now to determine this value, all we need to do is to find this value of the L, find the value of sine theta, find the value of r squared, and we are done. So let's look at a typical example of how to apply this formula. Now we have a conductor of length 2q, which is split into q and minus q. Now what you notice is that I assume this point to be the center of the length. So we have q up and minus q down. We are interested in finding the magnetic field at this point P along the x-axis. Then this q lies along the y-axis. Okay, so this r is a vector position, and which is determined by y squared plus x squared. Now from the formula, Biot-Savart formula, we recall that our dl is equal to dy, because the dl is this small change around this side, is in line with our dy. So dl is equal to dy. Then by the time you substitute this value into this original, it becomes dB equal to mu naught I 4 pi sine theta all over r squared dy. Now that we know this, we need to find out the value of sine theta and the value of r squared. The reason why we want to find out the value of sine theta and r squared is because we want to find them in terms of known parameters, not unknown parameters. So we'll move on to the next slide. From there, we recall that our sine theta is equal to x all over r. If you remember, if you go back to the diagram, sine theta is equal to x all over r, which is same thing as x all over x squared plus y squared, where our r squared is equal to x squared plus y squared. So if we substitute this value and this value into the Biot-Savart law, we have this expression. So we have mu naught I all over 4 pi x all over x squared part. So this part is the sine theta part, multiplied by 1 all over this part is the r squared part, then multiplied by dy. dB is equal to mu naught I all over 4 pi. You multiply x with dy, becomes x times dy. You multiply this by this, it gives you 3 x squared plus y squared 3 over 2. Recall that this expression is the same thing as this one, 1 over 2. This one is raised by 1. So when you add the indices, it gives you 3 over 2. So the next slide, we have to determine the value of B, we integrate both sides. So you remember, this one is dB. When we integrated dB, it gave us B. Now on this side, we integrate this part. We are moving from minus q to q, and because of that's the length of the wire, we have this expression. So to solve this particular, to integrate this particular problem, we make this substitution. Y is equal to x tan theta, where dy is equal to x sec squared theta d theta. Okay, so the next thing is B equal to mu naught I all over 4 pi. Then we substitute everything into this expression. From this expression, we assume that this one is K, which we have here. we still leave our q and minus q, despite the fact that we have changed it from dy to d theta. Okay, so from here, we'll factorize x squared out, and that x squared will cancel this square roots, and by the time you multiply raised to power 3, it gives you x cubed. We are left with 1 plus tan squared theta. 1 plus tan squared theta is sec squared theta. The sec squared theta will cancel this squared, and by the time you multiply raised to power 3, it gives you this. This one is still remains the same. From this expression, you can take care of this and this. Take care of this and this. You are left with 1 over x. Remember, when you take this one out with this, you are left with sec theta. And sec theta is similar as 1 over cos theta. So cos theta goes up and you have this expression. So x is independent of theta, so we bring it out. So it becomes k all over x, integral of cos theta d theta. But take note, our q is not in this. We still leave our q that way. So we'll move on to the next slide. Okay, from here, we integrated our cos theta, and it gave us sin theta. And from our sin theta, we'll recall that the substitution we made was y equal to x tan theta. And from this expression, we can tell that this theta is something as y all over x square root of y squared plus x squared. That's the relationship between this expression from this angle. Now that we already have our sin theta, we can find the value of sin theta from this expression, which is opposite all over hypotenuse. So wherever we see sin theta, we'll replace with y all over x squared plus y squared, still leaving this one. So we have moved it back from sin theta to the y. So we can now substitute this q back into this y, which is accepted. Okay, so we take our limits. Wherever we see y, you put q, which is this one and this, minus wherever I see y, you put minus q, which is this and this. At the end of the day, we simplify this one by saying minus and minus gives plus. So we have 2q all over square root of x squared plus q, k all over x. So our b is equal to this expression. So finally, we have our b is equal to mu naught I all over 4 pi x dot 2q all over this. So this is the expression for the magnetic field of a current carrying conductor at any point away from that conductor. So magnetic field of a short wire, and this one is for a short wire of length 2q. Now if we now consider for an infinite long wire where q is far greater than x, in that case q is assumed to be far greater than this. When you add this one to this one is insignificant. So that if you add this to this, it still gives us q squared. So if you take the square root of q squared, it gives you q, which is this q. So q takes care of this q, leaving 2. 2 takes care of 2, leaving 2. So our final b is equal to mu naught I all over 2 pi x. This is now the magnetic field at any point away from an infinite long wire. Thank you for watching. I hope you enjoyed this class. Please subscribe and share. Thank you.